So it's my pleasure to introduce our next speaker, Ercan Alp from the Ercan National Lab, who will give us an insight to the Sector 3 changes that happen as the APS-U upgrade is approaching. So if you could please unmute yourself.
Good evening, everybody, or good afternoon. I'm connecting from beautiful Istanbul. If you're feeling jealous, you should be. I will talk about nuclear resonance scattering at the upgraded ring. That's my focus. And I will talk about some of the new things we are developing for the high pressure and geophysics community. So my talk obviously is a long-standing collaboration between myself and Jiong Zhao, Michael Hu, who are currently staff members at the 3ID. We were lucky recently to have Barbara Labina, who joined us, who's providing us a real push for connecting diffraction with spectroscopy. And my PhD student, Mark Pavlik from NIU, Northern Illinois University, who's developing a new technique. So nuclear resonance scattering in the Western Hemisphere performed at the APS. So in that sense, we are unique. But we have competition in Germany, Petra 3, ESRF, in Grenoble, and Spring 8. And soon we will have two new beamlines joining, one in Beijing and one in Novosibirsk. So there will be 6 places to perform nuclear resonance scattering measurements. So there are 2 major scientific programs for nuclear resonance scattering at sectors 3 and 30. The nuclear resonance scattering program is comprised of the synchrotron mesopar spectroscopy, which provides you hyperfine interaction informations, nuclear resonant inelastic X-ray scattering, which provides sound velocity and thermodynamic properties, where we conduct SMS and NRIX simultaneously with X-ray diffraction. So this new combination with the new detector allows us to do in situ diffraction measurements under high pressure and determine many properties that are of interest to geophysics community. Furthermore, we have strengthened our programs with an online Raman system, thanks to a generous support from Compress. We have developed membrane DACs, again, thanks to a strong support from Jessicars and from HPCAT. We have laser heating, and we also have cryogenic cooling, so we can adjust temperatures between 10 and 3500 Kelvin. In addition, some of you have found momentum resolved inelastic scattering at 30ID useful for single crystal work. And main scientific output we have is speed of sound, isotope fractionation for geochemists, that's of interest, valence of the mesopar isotopes, phase fractions in heterogeneous samples, texture, and hyperfine parameters as a function of pressure, temperature, and composition. Furthermore, we also provide microscopic imaging using the mesopar microscope. So the nuclear resonance program at the APS-U era will continue 2024 and onwards. And I can see that this program, which is already well established, is a unique source of spectroscopic and microscopic information on complex and heterogeneous materials, still will be a wide range of scientific disciplines, including geology, geophysics, geochemistry, people who are studying meteorites and asteroids, to some inorganic chemists, bioinorganic chemists who are studying proteins and model compounds, catalysts for oxygen and hydrogen and nitrogen reduction reactions, which are industrially very important, emerging quantum materials, where superconductivity and magnetism can coexist, single molecule magnets, the new thermoelectric materials whose transport properties can be adjusted with pressure, magnetocaloric materials, and organic processes that leads to biomineralization. So we have delved into each of these fields with your help with your community, not on ourselves, but with your community. And you bring the best problems to us, and we are very lucky to be in that position. So in the APS-U era, the two programs will continue. The synchrotron mesopar spectroscopy and the nuclear resonant inelastic X-ray scattering will continue. But hopefully we will provide you two new tools. One is nuclear resonant time domain interferometry, which you have not seen until now. And the other one is the mesopar microscope, which we occasionally mention. The first of these two methods are well established, and they found their use in the fields mentioned above. But TDI, the nuclear resonant time domain interferometry, is currently under development. The main difference of nuclear resonant TDI from the other methods is that it's applicable to materials that do not contain nuclear resonant atoms. So you are freed from iron, presence of iron or other resonant atoms, but also it frees up for liquids. So if you are interested in melts, if you are interested in glass transitions, if you are interested in diffusional liquids, we can provide you a new method that will give you relaxation times as a function of temperature and as a function of momentum transfer. So mesopar microscopy and TDI will gain most, because mesopar microscopy will gain because of the spatial resolution can be reduced to under 1 micron level with full intensity of the X-ray beam. So there are two obvious advantages that you can imagine in the APS-U for nuclear resonance scattering. One would be the reduced beam size due to the reduced horizontal emittance, which we will be able to go under 1 micron beam. The other one is the increased current from 100 to 200 milliamp. So focusing the X-ray beam to micrometer levels will bring new opportunities, you can imagine, in high pressure physics and in mesopar microscopy. For example, NRS proved to be a good method to measure melting point of iron and iron alloys, which are of interest to people who are studying Earth's core. There are many materials which you would like to try in addition to pure iron. And the best way to measure the shear and compression sound velocities before melting and the melting point is nuclear resonance scattering. And by reduced beam size, you will avoid pressure and temperature gradients, which will help you to understand your data a little closer to the real conditions. So with the pressures going up to 3 megabar, I think we will to provide you also an opportunity to study super Earth-like exoplanets, and you can bring your minerals that are under those conditions. So another advantage of the expected advantage of the APS-U obviously is the increased current. With going from 100 milliamp to 200 milliamps, we will be able to provide you experimental conditions that are more realistic. For example, most of the proteins we study require several millimolar loadings, so we can probably reduce them. And also high energy vibrational modes of iron carbon, iron oxygen, iron hydroxyl, and so on. We might be able to provide you those small vibration, small displacement oscillations, a better picture of those. Studies of natural minerals such as meteorites, rocks, banded iron formations, and samples where isotopic enrichment is not possible, like meteorites, for example, will all benefit from increased current. So better quality data will enable better comparison with improving theoretical predictions like DFT and molecular dynamics. So we are quite excited about the upgrade. But there are also some issues that are remaining with upgrade, and I need to bring them up because there are very few champions of those issues. When you see APS picture, the way I see it is actually the one on the left, the 24 bunch filling mode. This is the standard operating mode 65% of the time. And the distance between the two is 153 nanosecond, which is miraculously close to 147 nanosecond, which obviously have something to do with iron resonance. So this 24 bunch singlet mode was very unique to APS, and in the last 25 years provided us an opportunity to publish over 500 papers that are very unique to each field. We also have 2 weeks per cycle, a hybrid mode where 16 milliamp is put on a super bunch and the rest of them were put on a 7-8 septuplets. So we can excite the nuclei with this and follow 1.1 microsecond very nicely. So this hybrid mode is also going away. Now, this makes it very hard for those of you who are doing time-resolved nanosecond or picosecond time-resolved experiments. So this is an issue. The 153 nanosecond gap between the bunches were ideal for iron-57 and SMS. Yet, this 153 nanosecond was not fully usable. APS never reached a clean fill structure, namely the bunches between following this main bunch and the 2 bunches before and 2 bunches after. Each bunch is 2.8 nanosecond separated, were never clean. APS's injection system failed for 25 years to provide us a clean beam. We complained about this early on for the first 10 years, then I got tired, and every time they promised us to fix it, so I realized that this is a birth defect. And one wonders what kind of birth defects we will have at the APS-U because nobody can guarantee. So we brought this issue up many times that the 48 bunch mold, which will allow us 76 nanosecond time, may also suffer from losing the first 25 nanosecond, which will be devastating. So we brought this up, and so far APS has made no measurable or concrete commitment for bunch purity. There is no plan A, there is no plan B, other than saying that, oh yeah, we would like to fill it clean. So that will not work. And if you are interested in time-resolved studies, MESPAR or otherwise, you should be worried because I am worried. And I brought this up, and so far I have not received a response from them. So this is an issue that is of concern for the future of not just nuclear resonance scattering, but people who are doing time measurements. So coming back to relationship between our beamline and compress, I can assure you that this is the most profitable relationship one could have, both from our perspective as well as from compress's perspective. About half of our users come from the compress community. And with the support from compress community, we are constantly able to provide you new tools. For example, if you come today, you will find a new Leica microscope at our beamline. You will find an online Raman system to read out the pressure at 100 GPa range. And you'll find a beautiful Dectris detector, which is brand new. So, of course, APS has supported the purchase of these, but so did the compress. And with the collaboration of the two, we were able to get upgrade our beamline ahead of the real upgrade. And so for that, I want to thank Mark Rivers and Vitaly Prokopenko to help us both with the detector and with the microscope. So Barbara Lavina, who is the real diffraction person, set out to make this detector work and work well. So she was very adamant about keeping the beam stop as small as possible and keeping the beam as clean as possible. And we were able to get beautiful diffraction patterns from the Hayabusa return samples last July. So we are very excited to continue this work in coming months. So I'm going to skip this, and I will mention a few things about the MESPAR microscope and the work we are doing for minerals. MESPAR microscope is a system. Let me show you what it looks like. It's our standard beamline, monochromators, high resolution monochromators, focusing mirrors, sampled where two detectors, Enrix detector on the side and SMS detector on the forward, with a reference sample to measure the isomeric shifts. So what do we do with that? Well, I started this work in about 2010, just out of curiosity, because I was so jealous of Sector 2 guys who were producing beautiful images, and we were looking at just one-dimensional data. So one day I decided that I'm going to put a meteorite, which I obtained from the museum in New York, and some samples from the Smithsonian. And here you can see on the left, the optical image of a mineral, of a meteorite, and the corresponding iron image of the same mineral. So if you go to several different locations on this mineral, on this iron-containing parts, you can get nuclear forward scattering information, and you can separate kamacite from troilite, for example. And furthermore, you can put the detector on the side and record the phonon-dense states, which will allow you to determine the temperature dependence of the isotope fractionation. So combined with the fluorescence data and diffraction data, we now have a very powerful tool to study mixed samples. So I looked at a couple of different meteorites just for the heck of it. And finally, somebody handed over me Chelyabinsk meteorite, and I looked at that too. So in the meantime, we set out a collaboration with the meteorite collector at Louvre and in Paris, Matthew Roscos, and Dr. Pierre Beck from Grenoble, where we combined our team and convinced Tomoki Nakamura from Tohoku University to include us in the Hayabusa mission. To qualify for that mission, we promised that we were going to look at a bunch of samples. For example, augite in the lab, in the beamline, 3+ and the blue one, 2+ iron. So we were able to get the ratios of 2+ and 3+ iron and the relative isomer shift and quadrupole splitting. So we repeated these measurements over the last year, 2 years, on various minerals where 2+, 3+ ratios. Here's the green one is the 2+, blue one is the 3+. This is a chrysotile at Thetford mine. And here you can see our beamline data, which I simulated through this red line, which corresponds to the actual measurement in the lab. In this case, we were lucky because we had enough samples. So here's a kronstadtite, a series of measurements on smectite, on San Carlos olivine, and so on. Pyrrhotite, Fe7S8, where we can identify the magnetic fields, the relative proportion of each phase, the isomer shift, and the quadrupole splittings. So these were really a series of measurements which we performed to show that we know what we're doing. And you're most welcome to ask for this data if you need in your future research. We're going to make this available to our users. So then they sent us some unknown samples, which we didn't know what they were, to test our ability. And we looked at magnetite. So basically, we are ready to look at now seriously in the mission. We started our work, and I promise you to give you more when we get there next time. So finally, I think I still have another 10 minutes. Is that right, Stella?
Yes, please continue.
Probably. I'd like to talk about time domain interferometry, even though the time I have will not be sufficient. So we're developing a new X-ray spectroscopic method to measure the slow dynamics of all liquids, melts, glasses, from continuum to down to atomic and molecular length scales. So this is a very heavy statement, but I can assure you that everything in there is doable, and we have done it. So when the new technique is considered usable, when a new technique is considered usable, I have to say that it has to be developed to a level where systematic studies as a function of temperature, pressure, composition at different length scales is possible within a reasonable experimental time. And to me, that experimental time is 1 week. So if you can come in and take 1 week data and maybe have a second visit, you should be able to publish and solve your problem. So what is it that we're developing? This figure is a loaded figure, and the physicists love it. And everybody else is sort of like, well, so if you look at the energy transfer range, we're talking about 20 orders of magnitude from 10 to the minus 15 to 10 to the 5 EV. So Compton scattering, for example, with the kilo electron volt energy transfers at hundreds of kilovolts is an extreme case where you can separate conduction electrons from the core electrons. X-ray Raman, you're more familiar with that. There is inelastic scattering is in the milli-eV range, but this region here is not so full with different alternatives. So the region we are covering now in the time domain interferometry is relatively empty region where XPC cannot reach because of the large momentum transfers, and yet we can provide you information there. So I will briefly mention the spectrum, the interferometer, since it's an interferometer, there has to be two arms. One arm is an iron foil where the nuclear resonance comes in, even though this is just to prepare the beam, has nothing to do with the sample, all right? Then we focus the beam to a sample where we connect start, so we can do temperature dependence of freezing. And then we have a stainless steel analyzer. Now you can, those of you who are familiar with it will immediately recognize that the iron foil, when it is magnetized in this form where the B is perpendicular to propagation as well as the electric field vector, iron will give you two-line spectrum, and it will give you a beautiful beat pattern like this, all right, where you have a continuous go down on an exponential scale. If you have a single line like stainless steel, you have a pattern that goes like this because there is nothing to beat against. If you put the two together, because of the long coherence length, these will interact and you will get a low and a high and a low and a high kind of a pattern. So what happens is that if this sample destroys the coherence, you're going to see a pattern like this. If the sample maintains the coherence by freezing, you're going to get a pattern like this. So these two extreme cases are the beginning and end of our interferometric signal. If you take, for example, glycerol and measure S of Q, nobody has managed to get data at this very low Q and at this very high Q because the count rates are so low. So our breakthrough is the one that we developed, allows us to actually measure across all Q points. And here's some examples. Here is two samples at 300 Kelvin. One is at 14 inverse nanometer transfer of momentum. The other one is at 2 inverse nanometer. So at 2 inverse nanometer, you're looking at a fairly large length scale. At 14, you're looking at average distance between the two glycerol molecules. So at this point, you see that the coherence is lost. Whereas here, since the coherence between stainless steel and iron foil is maintained, you see the high and the low pattern. So basically going from here to here allows us to make series of measurements where we can determine the relaxation time in nanoseconds as a function of Q and as a function of temperature. So the last slide I'm going to show you is this temperature dependence of the relaxation time from few nanoseconds to few hundreds of nanoseconds. So we asked ourselves, where is the limit? How far can we actually see? So Mark has gone through a very nice exercise and produced this beautiful picture where I'm going to quote a very famous philosopher. You will recognize him right away. I don't need to give his name. So even though the first 20 nanoseconds at APS is blocked, we cannot really see it, and the last 30 nanoseconds is blocked, the in-between window provides us sufficient selectivity where we can go from 1 nanosecond, the dotted line, to up to 10,000 nanosecond. So our sensitivity range in this new spectrometer covers 4 or 5 orders of magnitude.
1 minute.
So, yeah, where do we go from here? Well, now we are ready to offer you on any of your samples some measure of liquid-solid transformation as a function of distance and as a function of temperature and as a function of pressure. We can study glass transitions and crystallization behavior. We can go to biological solutions, studying proteins and protein dynamics. For geological melts, I believe that the first few users will see the benefits so that they will popularize. And we can also go to a diffraction peak, like in a ferroelectric material, and look at the shear modulus melting under phase transitions as a function of temperature or pressure. So I'm quite excited about the time domain interferometry. This is something we're going to offer you very soon as our first paper is published. And we expect that you will find many imaginative applications for this new method. So thank you so much.
Thank you, Ercan, for sharing all this exciting advantages that come along with APS-U, but also your concerns, which highlight how important the feedback from the community is. We have a recent head from Nenad. If you could please unmute yourself.
Go ahead.
Sorry about that. Yeah, nice talk and covering some of the techniques. But regarding the APS, the hybrid and the bunch mode, are you getting feedback that they're just not interested? Is it a feasibility thing? Is it money thing? Is it, what, does this community, can this community help? Or because we are also interested in some of the different timing modes.
I'm going to be uncharacteristically harsh. All right. I don't think I posed this question in many different forms to upgrade managers. And the answers I get are wishy-washy and not realistic. What I expect from them is the following. What is the bunch purity? And how are you going to get it? And if it doesn't work, what's your B plan? None of they are not deliverable. They are not among the deliverables. For example, APS project will succeed if it reaches a certain emittance, but the bunch purity is not among the success criteria. So you can put the two together and understand why my frustration is, because they are not committing themselves. They are very nice to me. When I go and bring this up, they are very nice to me, but they have been nice to me for 30 years, and the result is not satisfactory. ESRF, on the other hand, for example, they implemented a beam kicker into the accelerator years ago, and they provide nice, clean beam at 5 nanosecond levels. So why can't we do that? I don't know. And I have brought this up, and I ended up giving up basically after the first 10 years of trying very hard. So I don't think upgrade managers are even aware of this issue, how serious it is. And they don't appreciate the science. And if the community is not raising the flag, they will continue. Why should they care? Because the solution they have to find probably will cost a few $100,000 and serious engineering time. So I sympathize with them. It's not something simple they have to do, but this is something they have to do.
Well, thank you for the honest answer. I'm just so take a minute, but look, I mean, the money doesn't seem to be, on $1 billion or close to $1 billion project, the couple $100K doesn't seem to be too large. So I don't, I guess we can talk offline, but maybe some of this stuff is tied into their, CD4, and they don't want to tie into that, because then it's a performance thing. So maybe there is a potential to still have them look at it, maybe as a side thing. But anyways, thank you. Maybe we can speak offline when you're back.
It's a great discussion.
I mean, you look at the attendance list and see if there is an accelerator physicist listening to the talks to see what they have to do, and you will not find it. So we talk among ourselves, they talk among themselves, and that's basically there's no communication.
That's a great discussion. We have a question from Afu. If you could unmute yourself, please.
Yes, thank you, Ercan. So I'm interested in the use of the time domain spectroscopy, and you talk about the relaxation time that you can measure. Can you tell me in layman's language that what are the physical properties that we can derive from this type of measurements?
Yeah. Basically, the equations we have, I shied away from showing the equations, has a stretched exponential model built into the data analysis program. So you can determine for a given beta, you can determine, this is the Kohlrausch function. If you look at Kohlrausch function, you will recognize that this is a type of phenomena where the number of occupied states as the transformation takes place, like freezing or glass transition, gets less and less. And this is represented by a Kohlrausch function. So the information you will get is the relaxation time, which can be easily converted into viscosity. That's the information we're going to provide you as a function of length, which means we will measure dynamic viscosity rather than kinematic viscosity, even though we will measure the kinematic viscosity at very low Q. So the breakthrough we have compared to our previous attempts in this field is something that we developed that improved the efficiency of the system by almost factor of 100. And as such, able to go to very low Q and very high Q, independent of the structure factor strength. So we will provide you viscosity at different length scales, at different pressures and temperature.
And when do you expect this capability to be available?
Next month.
Wow, good.
So that's very exciting. Thank you, Ercan.